Don't abandon all hope, because we're going to talk about discrete probability distributions and basic business statistics with your instructor, Dr. Todd Dane.
Well, hello and welcome to week 9 of our basic business statistics class. This is the week where we start dabbling in probability distributions. And this is also the week that we're going to get to go on spring break starting on Friday. So you have the test that is open right now. You can get started on that anytime. You have until Sunday to complete that at the end of week 9. But feel free to get started early on that, and then you can just enjoy your spring break when it begins. I'm looking forward to spring break. You notice I have my Hawaiian shirt. Planning on sitting on the porch now that the weather has turned around. It's gotten nice again. I'm going to enjoy some time on the porch, wearing my shorts, wearing my Hawaiian shirt, and just getting to do some fun things on spring break, things I don't get to do all the time. I want to, probably like you, I just want to enjoy the time. I'm going to be reading some statistics books that I want to read. Right? Not the ones I have to read for class, but the ones that I have had sitting by my bedside table wanting to read. Been catching up on some logistic regression, for instance. I get to do some fun things like that for once, rather than just having to, deal with probability distributions. But that's going to be okay. So I hope that we all enjoy spring break. But in the meantime, we're going to talk about probability distributions beginning with random variables, a numerical description of the outcome of an experiment. It's what we call X. We use the letter X to represent a random variable. And there are two kinds of random variables that we're interested in. The discrete random variable, which may assume either a finite number of values or an infinite sequence of values. And before I unpack that, I'll also mention the continuous random variable, which may assume any numerical value in an interval or any numerical value in a collection of intervals. That will be our topic for next week. So this week, we're only going to focus on those discrete variables. And let's start with a discrete random variable with a finite number of values. Perfect example, this class. So we have 4 blocks in this class, and each block ends with a test. So if I ask, how many did you pass? The options are 0, 1, 2, 3, and 4. I could also ask, how many did you get an A on? Or how many did you get the grade that you were hoping to get? Or how many did you get at least a C? I could structure the question in multiple ways, but no matter how I structure that question, the answer options are always going to be the same. 0, 1, 2, 3, and 4. So when you think about a discrete variable, think of whole numbers. The numbers can only be whole numbers. You can't have passed 1.3 of the tests. You have to pass a value that is represented by whole numbers. A discrete random variable with an infinite number of values could be something like our dog toys data set. So remember, one of the questions that was asked was, how many toys do you own? It's still going to be whole numbers. However, the values could be 0, 1, 2, 3, 4, 5, but there's no upper bound. Certainly that is defined by the question. It could theoretically go to infinity. So we're going to be using whole numbers in any type of discrete probability distribution. And those values may or may not have an upper boundary, which is what qualifies them as either being finite or being infinite. A continuous variable, and again this is our topic for next week, could be something like filling up a sports drink can. How many ounces of fluid are in the can? The maximum, according to the machinery, is 16.1 ounces. So how many ounces are in the can? Theoretically could range from 0 all the way to 16.1. It should be some kind of value in between that range. Or you're operating a store. I just picked a bonsai store for no reason other than I happen to have a picture of a bonsai tree easily available. Any kind of store, any kind of business. How many minutes between each customer's arrival? There may be stretches of time when no one shows up. And there may be other times when 2 or 3 or 4 customers show up at almost the same time. There's very little time in between when one arrives and when the next one arrives. This value can assume any value greater than 0. 0 being our lower bound, but an infinite upper bound. Now we'll talk about this type of distribution next time. Right now we're going to talk about discrete probability distributions and start with expected values and variance. An expected value, when we talk about a probability distribution, is the mean. And it really is a weighted mean. So an expected value is a measure of central tendency for a random variable. In this example, I have sales and the probability of making a sale of 0, 1, 2, or 3 sales. The weights are the probabilities. So if we were going to calculate a mean, we would multiply the sales number by the probability, and we would use that for calculating our mean. And we're going to get a chance to do that using Excel here a little later. The variance and the standard deviation. Variance is a measure of variability for our random variable. It is still a weighted average of the squared deviations. Remember that a deviation score is x minus the mean. So once we've calculated a mean, we can subtract the mean from each of the sales numbers, square those values, add them up, divide by the total number, and that's going to give us variance. The standard deviation, therefore, is the square root of the variance in the same manner as we had calculated square root using any other distribution of numbers. This week I've created an Excel tutorial that is titled Probability Distribution Week 9. And there are multiple tabs across the bottom of this Excel tutorial. We're going to start with the expected value tab. It's going to look like this with just the blanks. We will be learning the sum product formula in order to use these techniques. The sum product means multiply one value times another value and then add up the totals. So here's how we would do this. The first thing that we need to make sure is that all of our probabilities add up to 1. So we could check that by going to cell B8 and we would type equal sign sum B2 to B7. And sure enough, our probabilities add up to 1, so we're good for this next part. Now we're going to create the mean. In cell B10, we're going to use the sum product formula. So it's equal sign, sum product, open parentheses. Our first array would be A2 to A7. And our second array is B2 to B7. This gives us an average of 1.5. And that was calculated by multiplying the sales figure times the probability. That product is then added up or summed, giving us a total of 1.5. So that means that we expect that the average sales will be 1.5 sales per day. Now we can calculate the squared deviations and again use the sum product. So the squared deviations, x minus the mean. Our formula therefore will be equal sign, open parentheses, A2 minus B10, which is our mean. And be sure to anchor or make this an absolute reference by using either Command T on your Mac or F4 on your PC. That's the dollar signs around the B10. Close parentheses, and then we want to multiply that by itself or square it. So caret 2. Hit return. Now we have a squared deviation for our first set of sales of 2.25. And we can drag our formula down to C7 to calculate these squared deviations. Now we're going to use the sum product on the squared deviations to get the variance. So in cell B11, type sum product, C2 to C7, comma, B2 to B7. And this gives us our variance. Remember, variance is a squared value, so we want to unsquare that, take the square root of it. So now in cell B12, square root of B11 gives us our standard deviation. And we would interpret this by saying the variance of the daily sales is 1.25, standard deviation of daily sales is 1.118. So next we're going to talk about these discrete probability distributions. A probability distribution describes how the probabilities are distributed over the values of the random variable. So if you look at this example, we see values that can range from 0 to 8. A probability function is the probability of each value of the random variable, which is notated by the fx. There are two conditions that we need to meet to use this. The first is that these probabilities must be greater than or equal to 0. So you notice there is a 0 probability for the x value of 8, but there are no negative values. And the second required condition is that when we add up all of these probabilities, they must add up to 1. Now there are two ways that we could assign probabilities. We could use the classical method, the subjective method, or the relative frequency method. Or we could mathematically define using either the uniform distribution, binomial distribution, Poisson distribution, or hypergeometric distribution. And that is what we're going to do now. We're going to start with this uniform distribution, which will be the first discrete probability distribution that we'll learn about. And it is the simplest. This best example for flipping a coin or rolling a die. The discrete uniform probability distribution. The function is 1 over n. Flipping a coin. Coin has two sides. The function or the probability would be 1 over 2, or 0.5. There is a 0.5 probability of getting heads, 0.5 probability for getting tails. Same logic for rolling a single die. It has 6 sides. You roll that die. The options, the probability of any side coming up is 1 over 6. So n is the number of values the random variable may assume. 2 sides to the coin, 6 sides to the die, 52 cards in a deck. And the values of the random variable should be equally likely. The coin is fair, the die is fair, the cards have been shuffled thoroughly. The second distribution is a bivariate distribution. Bivariate means 2 variables. Bivariate probability distribution is the probability distribution involving 2 random variables. Now we're not just rolling 1 die, we're rolling 2 at a time. And each die could have an outcome of 1 to 6. So we would consider the outcome for die number 1, and then the probability for die number 2. So each outcome consists of 2 values. That's what makes it bivariate. We're considering both of those die together. What this would allow us to do is come up with our range of possible outcomes. So if there's 2 die, what would be the smallest number that we could get in the combination of 2 die? It would be a 1 on die 1, a 1 on die 2. Smallest number value would be 2. What will be the largest number? A 6 on each die, total of 12. But what value would have the most ways of getting to this value? The value for 7 we could get to as a 6 and a 1, a 5 and a 2, a 4 and a 3 and a 4, a 2 and a 5. So there are many ways to get to 7. So we would expect to see 7 occurring more commonly with this bivariate distribution than we would expect to see rolls of 1 or of 12. So now we can examine the relationship between these random variables. For this, I'll use the example of a car dealership. The Florence car dealerships, there's 2 in town. We have Ghibelline Motors and the Guelph Coach Works. The Ghibelline Motors is a little larger. They sell more cars on any given day or week. And so their range of cars they would sell runs from 0 to 5. And this is based on observing how many cars are sold each day for 300 days. The most number of cars that they sold on any day was 5. For the Guelph Coach Works, the greatest number of cars that they sold on any given day was 3. So we have 2 variables, the sales for each of the dealerships, giving us a bivariate distribution. So you can see what we've started with are just some raw numbers. the number of days in which both dealerships sold 0 cars was 21. The number of days in which Ghibelline Motors sold 1 and Guelph sold 0 was 30. The number of days when Ghibelline sold 0 and Guelph sold 1 was 21. The number of days in which they both sold 3 was 3. And all of these values added together add up to 300. What we would then do is divide each one of these sales numbers by 300, and that's where we're going to get our probabilities. What is the probability that both sold 0? It's a 0.07. The probability that both sold 3 would be a 0.01. There's one other thing that we would want to get in order to create our frequency table out of this, and that would be the number of ways that we could get to sales of 0 or 1 or 2. So if you look on the diagonals, you see that there are many ways that we could get to 3 sales. One is the first dealership sells 3, the second sells 0, or one sells 2 and the other sells 1, or the opposite of that, 1 and 2, or 0 and 3. So there are 4 options for getting to 3 sales. And each one of those has a probability associated with it. We would add up all those associated probabilities, and then we could put those into a table that looks like this. Our column, which we're using S to stand for success or sales, ranges from 0 to 8. The sum of all the probabilities to get to any of these sales figures are added up in the second column. And then we can multiply the sales figure by the probability to give us the values that we need to add up, divide by 8, and get to our sales figure. So it's a 2.6433. We would say that the average sales for both dealerships is 2.6 cars. And then we could create our deviation scores by subtracting the sales figure from the mean. And then we would square that value, add it up, divide by 8, and it gives us our variability. Take the square root of that, would be the standard deviation. And a binomial distribution, different than a bivariate distribution. Binomial is referring to the number of outcomes. So we use a binomial distribution when there are only 2 outcomes available. 4 properties of the binomial experiment. The experiment consists of n number of identical trials. Think of flipping the coin. You flip the coin, it's identical to the next flip of the coin. There are only 2 possible outcomes, which we would call success or failure. Let's say we were keeping track of the number of heads that were flipped with each flip of the coin. Number 3, the probability of a success and the probability of a failure do not change from trial to trial. They are independent, so that the flipping of the coin when it comes up heads on this flip has no effect on what the coin will flip in the next trial, being independent of one another. So if we have satisfied all of those, let's use this example. When a customer visits the Divine Comedy store, the customer will either make a purchase or not. And you could apply this to any business. Dante, the owner, knows from experience that the probability of any one customer making a purchase is 0.30. This is from historical sales figures. 3 customers, Virgil, Beatrice, and Bernard, come into the store. What is the probability that 2 of them will make a purchase? What we would first need to consider are the facts that we have available to us. We know the probability of any one person making a purchase is a 0.30. We know there are 3 customers who have entered the store, and we're interested in the probability of 2 of them making a purchase. Now we could start this very simply by just taking the first probability, multiplying it by the second, and then the third person doesn't make a purchase, so that's 1 minus the probability, which of course is 0.3. So it's 0.3 times 0.3 times 1 minus 0.3, which computes to 0.063. That is the probability for just 2 of them making a purchase. But remember, there are 3 different ways that we could arrive at that outcome. The first 2 people make the purchase, the first and the third, or the second and the third. each of which has a probability of 0.063. I can also use the Excel tutorial on the Binomial tab to illustrate this outcome. I'm going to do this twice. In one example, we're going to have 3 people enter, and we'll use our probability of success and figure out the binomial probabilities. And in the second example, 10 people, 10 customers, and the probability of success will stay at a 0.3. And we'll also use cumulative probability for this example. So number 1, the number of trials or customers is 3, and the probability is 0.3. I've created a table with 0, 1, 2, and 3 as my x values, and my probabilities I would get from, I would go to C5, and using the binomial distribution, I would type equal sign, BINOM dot DIST for binomial distribution. So I want to begin by referencing the x value, in this case B5, comma, and then E1, which is the number of trials. I want to make that an absolute reference, put the dollar signs around it. E2, which is the probability of success, again, anchoring it, dollar signs around it. And then false, which is going to just give me the probability for that outcome. Close parentheses, and I've created a function value. It's a 0.343. Great. I can now drag that function down, and I've completed my table. So what is the probability for 0? It is a 0.343, or the probability for 3 is a 0.027. What if there are 10 customers? Well, if the probability of any particular person making a purchase is still the 0.3, I can fill in my probability table ranging from 0 to 10. Starting in cell H5, I would type equal sign, binomial distribution, open parentheses, G5, which is the first sales number, J1, the number of trials, J2, the probability of success, both of those as absolute references, and false. Close parentheses. Now drag that formula down. I've filled in my first column. The false option gives me just the probability, but sometimes I want to get the cumulative probability, adding up all of the scores up to that point. To do that, what I would start by doing is I'm going to go to cell H5 and just drag that one to the right and create a duplicate, except I'm going to have to clean this up a little bit. So I'm still using the binomial distribution. I'm going to make sure I'm still referencing G5. The J1 and J2 have been made absolute references, so those don't have to change. But I will change false to true. Having done that, I can drag this option down, and I've filled in my cumulative probability table. So what is the probability given 10 customers that at least 3, or let's say 3 or fewer, will make a purchase? I have a 0.64, 6 or fewer, 0.98. So that brings us to the Poisson distribution. Poisson, in French, means fish. You may remember one of my favorite scenes from The Little Mermaid, the Disney classic, was the French cook singing about le poisson, singing about cooking up fish. Poisson distribution is used when estimating the number of occurrences over a specified interval of time. And it could be over any specified interval. We just have to make sure that that interval is consistent. It is a discrete random variable that may assume an infinite sequence of values. So they're going to be whole numbers starting from 0, 1, 2, 3, 4, 5, all the way up to infinity. 3 properties of a Poisson experiment. Number 1, the probability of the occurrence will be the same for any 2 intervals of equal length. So over any 15-minute period, the probability of the occurrence is the same. Number 2, the occurrence, or non-occurrence, in any time interval, or space interval, is independent of the occurrence in any other interval. So again, our independence, that what is happening in one 15-minute time frame is not influencing the following or the preceding. The mean and the variance are equal, which is unique to this Poisson distribution. So here's some examples of when you might use a Poisson distribution. The number of knot holes in a 14 linear foot piece of pine board. So when you go to your favorite big box stores to buy a 2x4, counting the number of knots in the length of that board, we could use the Poisson distribution to figure out an average. The number of vehicles arriving at a toll booth in a single hour. The number of leaks in 100 miles of pipeline. Or, in a real-world example, Bell Labs used the Poisson distribution to model the arrival of phone calls. And this might be very beneficial as you're designing your phone system. The Poisson distribution, as well as any of the distributions that we're talking about, when we use them, we will find that they will form up into this normal distribution. So the distribution of sample means will always form a normal distribution, regardless of which underlying distribution we're using. And so when we talk next time about the normal distribution, this is going to become a very important point. We'll stress that when we get to that. So here's my example with the Poisson probability. Charon takes 15 minutes to ferry souls across the river Acheron. Arriving souls must wait when they reach the riverbed. So Charon has calculated that he ferries an average of 10 souls across the river for each trip. What is the probability of 5 souls arriving in the 15-minute period of time that Charon is making a trip? Well, let's use this example and see if we can apply the Poisson distribution using Excel. Click on the tab for Poisson, and here's how we would start with our calculation. So first of all, we need a mean. Well, the mean was estimated at 10, an average of 10 people making the trip each time. And so we would use that for our probability values. Again, Poisson distribution, so we'll start in cell C4. We type equal sign, Poisson, P-O-I-S-S-O-N dot D-I-S-T, and then open parentheses. We'll begin with the number of arrivals. So for 0, we would use B4. And then reference the mean. And because the mean will be used for each of these calculations, we want to be sure to make it an absolute reference, putting the dollar signs around. And then false, to just get the probability, close parentheses, and now we can drag that probability down the column, and we get the probabilities all the way down to 10 arrivals. Now let's do the same thing with the cumulative frequencies or cumulative probabilities. So drag cell C4 one to the right, and now we'll need to clean up this formula. So we still want the Poisson distribution with B4 as our reference cell. We still have E1 as an absolute reference, and change false to true. This is going to allow us to have the cumulative probabilities. Drag that formula down, and we have the cumulative probabilities along with our probability distribution. And the last distribution that we're going to explore is the hypergeometric distribution. There are three properties that we would want to know about. Number one, we would use the hypergeometric probability distribution when the trials are not independent, when one trial is somehow influencing another, and or when the probability of success changes from one trial to the next. So in this way, it is closely related to the binomial distribution, but it is one that we can use in circumstances where the binomial distribution assumptions have not been met. So here's this example. In the Divine Comedy store, patrons can sit in one of 9 circular areas. Each area holds 12 patrons. At a sold-out show, in other words, all of the circles have been filled, 5 poets sit in the first circle with the philosophers. Suppose Dante randomly selects 3 of the 12 patrons in the first circle for free drinks. What is the probability that exactly one of those 3 patrons will be a poet? So we have notations, X value will be 1, so the probability that exactly one of the 3 patrons will be a poet. There are 3 patrons selected. We selected 3 out of the 12 that are there. The number of poets in total, number sitting in that circle, are 5, and there are 12 patrons total. Some are poets, some are philosophers. So using the Hypergeometric tab in our Excel tutorial, this one will be a little more simple. The first thing that we want to do is make sure that we filled in the options. So we have a number of successes, or X, is 1. Number of trials, or N, lowercase n, is 3. Number of elements in the population that are labeled a success would be 5. That's the number of poets. The number of elements in the population total, there are 12 people sitting in this circle. And now we can calculate the hypergeometric probability, which we would do in D6, type equal sign, HYPGEOM dot DIST for our hypergeometric probability distribution. And then we'll enter these the next set of values in order. So D1, D2, D3, D4, and our last argument will be false, and that gives us just the probability value. And that number is a 0.4773. We can also get the mean and the variance and the standard deviation using formulas. For instance, in D7, we could use this formula. D2 multiplied by, and put this next part in parentheses, D3 divided by D4. D3 being the R and D4 being the uppercase N. That gives us the mean. And then we can also calculate the variance. The formula is a little more complicated, but it's one that we can type in. And that will give us the variance. The standard deviation is the square root of the variance. We just get the square root of D8. There's our mean, our variance, and our standard deviation for this hypergeometric probability. And that's what we're going to discuss this week for our discrete probability distributions. So before I wrap up, do you guys have any questions about the probability distributions that we've already discussed? All good? All right. Thanks for being here. Have a great spring break, and I'll see you guys when we get back. Be safe.